Right, thanks for having me. Thanks for the opportunity to be here and give this talk. So we have a number of very interesting technical talks on differential privacy coming up in the next few days. That's not what this talk is. This is a talk designed to introduce and motivate the definitions, tell you a little bit about some of the tools that you'll be hearing more about in the future talks, and hopefully get you excited about some of what we can do or may be able to do in the future with differential privacy. And I should mention also that almost everybody who's been involved in this work is in this audience. So if you have questions, the experts are here. That's great. So the motivation for this talk and for many of us being here today is that individuals have lots of interesting data. And we would like to be able to compute on that data. And I shouldn't have to work too hard to convince all of you that really there's a lot of data about all of us from all sorts of sources, held in all sorts of places at this point. So it's shopping data, it's financial data, it's health data, it's email, web search, social network, MOOC data. It's all sorts of data, and there's huge potential here. I mean, that's why we're here today. So whether you're interested in statistics or statistical correlations on that data, perhaps thinking about the genetic data, thinking about genotype-phenotype associations, or correlating medical outcomes with risk factors or events. Maybe you're interested, for example, like the census in publishing aggregate statistics. Maybe you want to do some sort of intrusion detection or other outlier detection in your data set. Or maybe you're just somebody who has a huge amount of data and you want to do something with it. Maybe you're a company with purchase histories or search histories and you want to use that to make good recommendations or change your strategy. You want to somehow make good use of the data that you have at hand. So there's lots of potential in these huge data sets of personal information. And also, everybody who has spent any time thinking about privacy has some favorite examples of how this can go very wrong. So my personal favorite example, which is by now old, is what I call the AOL search debacle. So back in 2006, in August, AOL Research, which maybe you don't even know ever existed, released 20 million or so keywords paired with anonymized user IDs for over 500,000 users over a 3-month period. So that's search histories of a huge number of people for a 3-month period. And if you use your favorite search engine, AOL Search or whatever it is, to look up AOL Search debacle and related terms, you'll get some interesting stories about it. But that's the basic story. This is a very well-intentioned release on the part of AOL Research intended to reach out to the broader research community and make data available. And they did think about privacy. So the relevant quote is that actually no personally identifiable information under some definition of PII was released. So it's not that they took my name and lined it up with each of my search queries, but rather they replaced the most obvious identifier, no email address or no name, things like that, with some unique identifying string. Now, of course, if you take a look at your own search history or someone else's, you shouldn't be too surprised that self-searching or other potentially identifying searches on name, on address, on social security number is very, very common. And even if you try and eliminate the most obvious of these, it can go wrong. So as in this case, AOL Search did try, and within a couple of days there was a New York Times article revealing the identity of one of the searchers, and subsequently many other people were identified. And there are some quite interesting search histories in the log if you take a look. So there are a couple of potential lessons from this particular instance of privacy gone wrong, and one of them is that ad hoc solutions to privacy problems are risky. The flip side of this, or the optimistic view, is that this is a huge opportunity for formalism. Now you might be saying, well look, first of all, I'm not that stupid. I wouldn't release anything that looks like this, and second of all, maybe this isn't really what I want to do. I'm not really interested in publishing a whole data set. I just want to make good use, publish some aggregate statistics, for example. Why should I be so concerned? So let's step back and think a little bit about what we might want to do with sensitive data. So we might, as in this example, want to take a database of individual sensitive information, for example, medical records, and produce some sort of sanitized version of the database that's useful for a large number of queries. But you say maybe that's not what you had in mind. Maybe what you have in mind is just producing some set of statistics on the database. Or maybe you want to fit a model. You want to do something somewhat sophisticated, but that feels like it's aggregation. Should you really have to worry about privacy? Or maybe you want to do something very simple. You want to take this database and you just want to output a single number. For example, what percentage of people in the database had cancer? That seems innocuous. Should you worry? Or maybe you want to do something that feels almost orthogonal to these sorts of goals, and you want to use your database of personal information to make decisions. Maybe you want to use it to decide policy decisions. Maybe, for example, you're trying to decide the locations of treatment centers for a disease that might be stigmatized, and you want to make the treatment centers convenient for the patients. Maybe you're, again, a company and you have information about people's purchase histories and you want to use it to make recommendations. So how can we think about making decisions, recommendations, more sophisticated, taking sophisticated actions based on sensitive data? So this claim of I shouldn't have to care about these privacy debacles because I don't want to publish all the data, I'd say, hold on, maybe not so fast. Certainly, in theory, you could have problems. And also in practice, we've seen there can be problems too. So one very nice example comes from Alexandra Korolova's work on Facebook micro-targeting. So in particular, back in 2011, when Alexandra was doing her work, it was possible, as an advertiser on Facebook, to specify the characteristics of the audience that you were interested in so finely that they would correspond to a unique Facebook user. And so then you could use this actually to discover information about individuals. So for example, if you were interested in the sexual orientation of some individual, you could run an ad campaign that was narrowed down to that one individual, and then you could do one version of it that said, also interested in women, and another version, also interested in men. And then when you got your statistics back from Facebook on which ad was shown, you would learn the existence of such an individual. And there were a number of other interesting, somewhat surprising, somewhat disturbing, revealing things you could do with this micro-targeting capability at the time. And this is an interesting situation because this is an instance of a system that was actually designed in some sense to help protect privacy. And it was a use of data that didn't involve explicit publishing of any sort of data version of the database, really not much in the way of statistics even. It was a very limited use of the data, but actually ended up being quite revealing. So this is another instance of getting privacy slightly wrong for not thinking about it quite formally enough. And so really I think the lesson here is that we have to be a bit paranoid here. We really need to pay attention to all uses of sensitive data. Anytime you touch the sensitive data and the result of touching it is public-facing in any way, you need to pause and think about what the consequences might be. Okay, so I guess the question all of this raises is, if we wanted to give a more formal guarantee of privacy, what should that guarantee be? What might we want to promise to the individuals in the database? So let me propose something. We'll try it out. So what if I were to offer you the promise that access to the output of my computation won't let anyone learn anything about anyone that they could not have learned without access? What do you think? Sounds pretty good. Some people sound pretty convinced. So, sounds pretty good, but let's step back for a second. So is this even possible? So I heard sure, and yes, of course it's possible. And the hint there is that, well, either privacy or utility separately is easy. What do I mean by that? What do you do if you want perfect privacy? Or in the database. What do you do if you want perfect utility? Publish the whole thing. Okay, so that's not really the question. The question is there a meaningful trade-off between privacy and utility? And that's the space where you really have to ask these questions. Is there a meaningful trade-off there? Okay, so let's try again. And let's maybe think about this in the context of an example. So what if we wanted to do a study about smoking and cancer? So we had a medical database with information about people's habits and their medical histories, and we wanted to publish something that feels fairly innocuous. For example, there's a correlation of blah between smoking and cancer. The problem is, what if somebody knew that some specific person, say Alice, were a smoker? Well, then as soon as the results of that study came out, you've learned something about Alice. Your assumptions about her have changed. Your prior has changed once you learn the correlation between smoking and cancer. And so Alice has been harmed, and in particular, you've learned something about her that you couldn't have learned without access to the database. So this is really too strong. And it's too strong in the sense that it's preventing us from doing things that we really actually would like to be able to do with our data. In some sense, the whole point of doing a study on these large databases of interesting, sensitive personal information is to have the potential of changing people's priors. You do actually want to learn something from the data. So it turns out formally, it's not possible to get a meaningful privacy utility trade-off under this definition. So what might we do? Or what might we promise? So let's try and focus on, well, what if what we wanted to do is output just a single number? What percentage of people in the database have cancer? If you wanted to do that and preserve some sort of notion of privacy, what would you do? Well, you probably realize that you need to introduce some sort of noise or randomness. And so maybe what you do is you take the right answer and you'd perturb it somehow. So maybe what you do is, instead of outputting the right answer, you'd flip some coins and get some sample from some sort of distribution, hopefully centered around or near the true answer. And then maybe what you'd like to do is promise something about this distribution. So maybe we can promise individuals that if they were to leave the database, then actually none of the possible outcomes of our mechanism would change probability by very much. And this is the intuition that we're going to formalize here. So we're going to think of a database as a set of rows, one per person. And we're going to be talking about sanitizing mechanisms or algorithms which probabilistically map from the database space to some outcome space. So you take a database and you return some outcome. And the outcome space can be quite general. So we might be interested in privacy for mechanisms that produce, for example, a single statistic, or maybe we want to produce sanitized data of some form, or maybe, again, we want to do some sort of policy decisions or more complex decisions. And in any of these cases, we can talk about properties of this mapping. And so the notion of differential privacy, which comes out of line of work of Denur, Nissim, Dwork, McSherry, and Smith, is its notion parameterized by epsilon. So we say epsilon, a mechanism, this mapping, preserves epsilon differential privacy if for any two neighboring data sets that differ on any one person's information, and for any outcome in the range of the mechanism that we might be interested in, the probability that the mechanism returns that outcome C under the first database is multiplicatively very close to the probability that the mechanism returns that outcome under the second database. And again, this is for any D1, D2, so feel free to swap the D1, D2 in this definition for symmetry. And this is really saying outcome by outcome, you're going to be getting almost exactly the same probability under any two neighboring databases. And again, that's differing in any one person's information. And if you prefer it, instead of this e to the epsilon, which is where the epsilon privacy parameter shows up, you can think of that as a multiplicative 1 plus epsilon. So let's sort of go back to this example of outputting a single statistic and try and interpret the definition there. So here we have a database of records, one per person, and we have some true answer, but under differential privacy, we're going to need to randomize. So our mechanism under a particular database is going to induce a particular distribution over a set of possible outcomes. And what differential privacy says is if we were to change that database by adding or removing a row, then the distribution that's induced needs to be very, very close to the previous distribution. And very close in this very particular sense, where if we were to look outcome by outcome, it would be multiplicatively close. So from the perspective of an individual, thinking about whether or not to participate in a differentially private computation, you can think about, well, maybe your concern is really about there's some possible outcomes of this mechanism that are really bad for me. Maybe this is, again, the smoking and cancer study, and you're worried about the outcomes that would result in your insurance premiums being increased. Well, what differential privacy is saying is, sure, you can focus on those outcomes, and you can look at the probability that they would occur if you provided your data to the study. But actually, if this study is being run with differential privacy, those outcomes will occur with almost exactly the same probability, even if you do not provide your data. So in some sense, you're sunk. The bad things are going to happen regardless of what you do. So, and actually you can formalize this notion from the perspective of an individual. You almost might as well provide your data. Yeah, question?
So in particular, if on a particular database C has measure 0, then it will have measure 0 everywhere if it's connected.
That is a perfect transition to the next slide. Yes. So under epsilon differential privacy, if there's an outcome that has probability 0, under some input, it must have probability 0 under all possible input databases. But we can relax that. And instead of just allowing this multiplicative factor difference, we can also allow an additive difference. And then we talk about epsilon delta parameterized differential privacy, where the epsilon controls the multiplicative and the delta controls the additive. And then we are able, potentially, to move from a 0 probability event to a non-zero probability event. Now, this relaxation could be troubling because of that. In particular, it allows you to design a differentially private mechanism, epsilon delta differentially private, where there could be some outcome which would allow you to make concrete inferences about the original database. You could potentially actually know with certainty something about the original database. So for that reason, we like to think of this delta as very small. And how small depends a bit on the setting. But the main reason that we think about moving to epsilon delta is because it enriches the space of mechanisms and strengthens, in some cases, what we know how to do. And you'll hear in the coming days about both flavors of privacy. And I guess I should emphasize here, When we move to the epsilon delta version of the definition, and we're comparing the outcomes, we're actually comparing any subset of the range here. So the probability mass in any subset of the range. So there are a lot of nice things to say about this privacy definition. I won't even get to say all of them, but let me just mention a few. So one thing that's very nice about differential privacy is that it's a property of the mechanism. So this is different from some other approaches to thinking about privacy. In particular, you can't take an outcome or a statistic in isolation and say that it is differentially private. You can say that the process that generated it is differentially private. And because we're talking about privacy as a property of the mechanism, differential privacy is able to avoid some of the problems that have plagued other approaches to privacy. In particular, the troubles that you run into from outside information. Because differential privacy is really not doing anything to model the outside information that's available to an adversary. And in addition, it's not really doing anything to model the adversary at all. So other than some work that specifically looks at computational differential privacy, work in differential privacy is independent of any assumption on the adversary's computational power. Okay, so the promise that we're going to be making to individuals is essentially if you leave the database, no outcome will change probability by very much. And of course now, hopefully, you're wondering, is this achievable in a meaningful way with accuracy? And luckily, for this talk, the answer is yes. Okay, so let's start with the simplest thing that we might want to do. What if we want to output, again, a single number based on the database? So what percentage of people in the database had cancer? As we said before, we expect that what we're going to have to do is some sort of randomness. We're going to have to sample from some distribution where we've added noise with some particular shape. And the question is really, what is the shape and how much noise do we need to add? And so it turns out that the relevant question here is, what is the sensitivity of this function that we wish to compute on the data? What do I mean by sensitivity? Well, I mean, if we look at any two neighboring data sets that differ in any one person's information, how much can that function change? Because that's essentially what we're trying to hide with differential privacy. We're trying to hide the change induced by any one person. And so if we have a measure of how much any one person can affect the output, actually we can use that to understand how much noise we need to add. So for example, if what we were interested in is a query that counted the number of rows in the database that satisfied a particular predicate, the sensitivity of that type of query would be 1. Because if we were to add or remove an individual from the database, the count of people who satisfied the predicate could change by almost 1. And so sort of the first tool in differential privacy is noise addition in the form of Laplace noise. So basically the result here from work of DeWork, McShardy, Siemens, Smith says that if you have a query F and you add scaled symmetric noise, so doubly exponential noise in the form of the Laplace distribution, where you parameterize the Laplace distribution by this dependence on the sensitivity and on the epsilon privacy guarantee that you want to give, then you achieve epsilon differential privacy. And so for those not so familiar with the Laplace distribution, in some sense the details don't matter so much. It's a doubly exponential distribution, and in some sense it's tailored exactly to what we need for differential privacy, because this is a distribution where if you shift it over slightly, it has the property that if you go point by point, the ratios and the probabilities maintain this multiplicative ratio that we need for differential privacy. Okay, so let's apply this naive noise addition and see what we can do here. So let's return to this idea of counting queries. So how many people in the database satisfy a particular predicate P? As I mentioned before, it has sensitivity 1. And therefore, if we want to preserve differential privacy for this type of predicate, we can add noise. It takes the form of Laplace 1 and epsilon. Okay, so we know how to answer a single numeric query when we understand its sensitivity. That's a starting place. But what if you want to do more than one query on your database? It seems quite natural. So there's some very nice observations that one can make here in the form of composition theorems. So the simplest composition theorem for differential privacy says that if you run an epsilon1 differentially private mechanism and follow it up by an epsilon2 differentially private mechanism, that overall this computation is epsilon1 plus epsilon2 differentially private. And actually this is fairly straightforward to prove, and you can also prove a similar fairly straightforward theorem, composition theorem, when we're in the epsilon delta regime. So in that case, both the epsilons and the deltas can be summed up to give an epsilon delta guarantee. But actually, in the world of epsilon delta differential privacy, a more sophisticated argument is possible. So here, actually, if you did k runs of an epsilon delta differentially private mechanism, you get a new epsilon delta differential privacy guarantee that doesn't need to scale directly in k times epsilon, but rather in root k, which is very nice. Okay, so now we have a sense that we can answer more than one question with differential privacy, and let's take a look at that. So if you want to answer a set of D queries, you can think of that as a vector valued query of dimension D. And so you can apply this composition idea and add noise that's now going to grow with the number of queries, where the parameter is now going to grow with the number of queries. So Laplace of D times the sensitivity divided by epsilon. And that's going to be in each component of your output. Okay, so the next question is somehow, is there anything more sophisticated going on? And you'd hope that there is. And here's the first hint that there might be. So let's think about histogram queries. So what do I mean by a histogram query? I'd like to output numbers for a bunch of bins. So I'd like the count of individuals in the database that fall in each of some number of non-overlapping ranges. These ranges could be, for example, ages. How many people in my database are between the ages of 0 and 5, 6 and 10, so on and so forth. Okay? And so, well, we already know how to answer a whole bunch of queries, which is essentially what this is, a whole bunch of bins. We could, again, use noise that scales with the number of bins. But actually, it turns out we only need noise that grows with epsilon, not with the number of bins. This is really the sort of first surprising result. So why is that? So the generalization of the sensitivity of a function to the case of thinking of a vector-valued function is to look at the max L1 distance. And so the question is, if I were to add or remove somebody from a database and run a histogram query, how many bins could change? Yeah, so it depends how we define neighbors exactly, and we're not going to worry about that. But depending on how you define neighbors, the answer is 1 or 2. Okay, and how much can those bins change by? 1. So we have very, very tight control, actually, on how much this vector of outputs can change between any two neighboring databases. And it doesn't depend on the number of bins. So actually, you're welcome to make your histogram as fine as you'd like, and that doesn't change the amount of noise that you need to add to each bin, which is kind of surprising. So I should also observe that there's a similar to this Laplace mechanism that we've just seen. There's a Gaussian mechanism, so you can add normally distributed noise. This is a result that I think first appears in work of Dwork, Kantopady, McSherry, Mironov, and Naor, observing that Gaussian noise gives you a guarantee of epsilon delta differential privacy. And there are various reasons why you might prefer Gaussians, including that they just may be more familiar to you. But so this is also nice to observe here. And here the sort of proxy for sensitivity is, instead of an L1 distance, an L2 distance. Okay, so we know now how to answer a single statistic under differential privacy. We know how to answer a handful of statistics under differential privacy. But what if you want to make much more significant use of your database? Maybe you really want to handle some exponential number of statistics. So first an aside here, since we're talking about big data, at least in my mind, data can be big in two ways. And maybe you can think of others as well. But the first is data can be big in terms of more rows, more individuals in your database. And intuitively, what we've seen so far is that seems to make privacy easier. Because effectively what we're doing is we're making the queries lower sensitivity in some sense. The answers are less dependent on any one individual when we have more individuals, intuitively. But data can also be big in the other dimension. More columns, more descriptors for each individual. And that, we'll see, seems to make privacy harder in the sense that there's more information about each individual, more queries to preserve, more to distinguish individuals from one another. And so big data can help us or can hurt us depending on which dimension we're talking about. And now we're going to move into the space where we start to understand a little bit more about when we have more queries to preserve. So basically, the goal that I want to talk about now is you want to take a database of sensitive information and use it to produce some differentially private object, which could look like data or not, where you can use that object to handle an exponential number of queries, sort of exponential in the relevant parameters of the database. So for example, maybe you want to handle some exponential size set of these counting type queries. You want to know what fraction of people in the database are over age 50, what fraction have a couple of different properties, maybe they smoke and have lung cancer, things like that. And you have a huge set of these questions that you want to answer on your database. So what we've seen from the tools so far, although I didn't highlight it, is that really with naive noise addition, we can effectively answer on the order of n squared queries, where n is the size of this database. And here we want to handle much more than that. So there's actually been a lot of work in this line, and I'm not going to talk much more about it, partially because I suspect John is going to be telling you much more about it in his tutorial. But there's been a lot of work trying to see what you can do in terms of the privacy utility trade-off, and also trying to understand how efficiently one can do it. So this is sort of the positive result side. There's also sort of a parallel slide to be shown that highlights John's results on the negative side. But what I want to highlight here is actually that there's evidence here that at least sometimes, in some sense, we can do much, much better than naive noise addition in terms of the number of queries that we can handle when we move to much more sophisticated techniques than simply adding noise. So in order to do that, I'm going to talk very briefly about two of these results, but we'll hear more from John, in particular about the results that leverage the connection to multiplicative weights. So in order to do that, I get to introduce one of the other sort of basic tools for differential privacy, which is the exponential mechanism of Mikshari and Talwar, which is basically the idea of exponentially weighted sampling. So what you do under the exponential mechanism is you define some space of possible outcomes from which you're going to sample, and you sample from it biasing towards the outcomes that perform well on some scoring function that you define. And so if you have a database D, the probability that you output a particular outcome C is going to depend on its score going to depend on the epsilon parameter that you have for privacy. It's also going to depend on the sensitivity of the scoring function. And it actually turns out that for the exponential mechanism, privacy is really straightforward. And the tricky thing, perhaps not surprisingly, is utility. So in order to prove that you get high quality outputs from the exponential mechanism, you need to show that you're able to concentrate your probability mass sort of highly enough on these high quality or high scoring outcomes, and you need to pick a good scoring function for that. And then in addition, you have some concerns about the computational issues, potentially computational issues in evaluating the scoring function and in doing the sampling from this distribution. So one example of a mechanism that looks very different from naive noise addition, that's designed to handle a large number of queries, is this work with Avram and Aaron. And the basic idea here is a combination of the exponential mechanism, which again is this idea for sampling from some complex output space, and an observation about sample complexity bounds from learning theory to guarantee the existence of a good output. So basically what's going on here is very, very simple. We have a database, and we want to somehow produce some object on which we can simultaneously answer some huge number of queries with accuracy that's very, very good, so very close to the answers on the original database. And the key observation that comes from learning theory is, well, what if we think about the question, forgetting about privacy for a minute, how big would a database need to be, or how many samples would you need from the original database in order to support all of those queries that we're interested in? So forget about privacy for a minute. Just ask the question, how much data do you need in order to answer all of a large number of queries well? And actually, this is a question that computational learning theory answers. And the answer is that it depends on the power or size or VC dimension of the class of queries that you're interested in, and also on the accuracy guarantee that you want to get. Sorry, this should be an alpha for accuracy, not an epsilon for privacy. So here, it turns out that you need a number of samples that depends on this VC dimension. And so what we say is, okay, so consider all databases of that size. All possible databases of that size. Yes, it's a very, very large number of possible databases. And apply the exponential mechanism, this exponentially weighted sampling, to sample from this space where the scoring function we use is some measure of how well each database performs on all of those queries of interest when compared with the original database. And it turns out, actually, one could show that this exponentially weighted sampling allows us to produce a small database in a differentially private manner that is good on all of the queries of interest with high probability. So this is really an information theoretic result that lets us create synthetic data that's simultaneously useful for a large number of differentially private queries. And the point here that I want to make is really that this doesn't look anything like noise addition. It also doesn't look anything like sort of local perturbation of the database. It doesn't look anything like sampling the database, really, even though there's some sort of connection to sampling results. It doesn't look anything like sort of swapping bits and pieces of different rows of the database. This is very different from what you might have done had you sat down with a database of information and tried to mask it for privacy. Yeah?
So, just to clarify, did you say that you pick VC dimension many databases, or one?
So that's the size of these databases that we consider as possible outputs.
So many different databases.
So we consider every possible database of this size. So it's a huge number of databases. So we fix the size, and then we say, well, it could have all entries that look like this possible entry, or it could have all of that plus, one other entry, of the next type, or it could have and fill in with every possible combination of rows that could appear in the database. So it's a huge number of possible databases. And we sample from that. And the distribution that we sample from is biased towards databases that do well on all of the queries that we're interested in, all of the queries in the class.
So will you or somebody talk about how you can do the sampling efficiently?
It's so...
We just want to be careful.
So yes, that is a very relevant question. I'm actually not going to talk about the efficiency in detail, but I will talk in the next slide briefly about a result that actually does perform well in practice. It doesn't look like this one, but it gets the same guarantees. But you're right on, this is not a computationally efficient result. And this is really an information theoretic result that started a line of work in trying to understand how does computational efficiency play into this question of the trade-off between privacy and utility. There's sort of another dimension to consider there. Yeah, but very fair question. So the result that I wanted to mention briefly, and I think John will tell you more about this result, is some work with Moritz and Frank, where we have a mechanism that, like the Blum-Leggett-Roth mechanism, is designed to preserve accuracy for a large number of queries. It's perhaps even simpler to describe and to implement, as you'll see when you hear more about it. And what's different there is that we actually implemented and tested on real data, where Frank gets most of the credit for that. And so it actually achieves the state of the art in theory. And what we see is that it performs well in practice and does so quickly despite some worst case news that you get from folks like John about computational difficulty. Sorry, John. Computational difficulty of these problems of simultaneously answering a large number of queries.
Sorry, there was a question there. I just have somebody else.
That's okay. You can't postpone it later. That's fine.
Okay. Questions are always welcome, though. Thank you. Sorry, I missed it. So I just want to give a brief preview because John will be talking much more about multiplicative weights-based techniques. So we have some sense that perhaps, maybe not formally in a computational sense, but at least practically, it seems that in real-world cases, we're able to produce even synthetic data, something that looks like data, that can simultaneously answer a large number of queries. And the reaction you might have to this is, well, that's fine and all, but what, you're telling me I have to know all my queries in advance? That doesn't seem very realistic. Maybe I want to ask a couple of questions, run a couple statistics on the database, and see what the answers are. And then run some more, depending on what the answers are. And actually, that's fine. So I haven't talked about it so far. So far, I've been talking about creating synthetic data where you have to know your query set in advance. But actually, there are results in the literature on interactive mechanisms. And basically, the idea here is that tools exist to answer a similar number of queries, even on the fly. And the key idea there is that you need to be, in some sense, correlating the randomness that you're using across your queries in a sophisticated manner. And so this is, again, something that I expect will come out in John's talk. Okay, so perhaps the next objection is, well, when you step back and you look at the results and think about it for a little while, perhaps you decide, well, actually, it just seems like differential privacy would add too much noise for my application. Or maybe you tried it out and you weren't so happy with the level of noise that differential privacy seemed to prescribe. Now, first of all, that could just be that you didn't pick the best possible mechanism, or there is a mechanism that nobody's come up with yet that would perform better. But let's suppose even that your objection is that there's some negative results that seems to apply in your setting that says that a particular level of noise is necessary. So I'd like to stop and really think about what it means. If you're in a situation where differential privacy seems to suggest you need to add a lot of noise, an undesirable level of noise, what does this really mean? So, at a very high level, what's going on is that differential privacy is connected to the robustness of the computation that you're trying to compute, as robustness to the presence or absence of individuals. And so the first thing I'd like to say, if you think that differential privacy would force you to add too much noise, is you should think carefully about whether or not this means that your computation is not robust. And if that's the case, you should really worry. If you're doing a medical study, and the results of that study depend crucially on the presence or absence of one or a couple of individuals in your sample, you should really worry about your study. But maybe that's not what's going on for you. Maybe what the message that you're getting is actually that you need more data to get your desired privacy utility trade-off. In that case, it's not so much that you should worry, but perhaps this reflection should give you pause, and you should think a little bit about, well, what does this mean in terms of what I should or could be promising to individuals, or what I can say about the quality of the study that I'm able to run. Or maybe you say, well, actually, the problem is that this differential privacy thing is really kind of too strong. In the sense that, well, I expect that on real data, the data that I actually have, that the function or the statistics that I want to compute will actually be robust. It's just that in the worst case, that they're not robust to the presence or absence of individuals. So this differential privacy thing seems to be just too demanding in terms of robustness. And it turns out this is a place where we really know how to do something. And so that's what I want to talk about next. So first, an aside, because I'm using the word robustness very informally, and it's a formal term to many of you, and I'll actually be using it in a couple of different ways. So I want to acknowledge that. So first of all, robustness in a differential privacy sense is not identical to statistical robustness. And in particular, robustness, as I'm going to be using it here, in the context of differential privacy, is really worst case. So it's worst case overall possible databases, worst case overall individuals that you might sub in or out of the database, worst case over the outcomes that you might be interested in. And so this is not robustness with respect to a distribution. But there are connections between the robustness in the differential privacy sense and robustness in the statistical sense. And we'll get there in a little bit. Questions? Yeah. Jerome, yeah.
Please. Well, I was just going to say that's an interesting argument, but I can think of some analyses, for example, if I was looking at a network trace and looking for a very subtle pattern in packets, where it's not a problem with my analysis being not robust, but it's still highly sensitive to particular changes. So in that case, I think there might be an inherent lack of utility possible.
And so that's also certainly possible. I think that's also a good observation to make. It's not to say that you then won't go ahead and do the study. But I think it's useful to understand in what sense is the study robust or not robust, and what are the privacy utility trade-offs? What are the promises that I could make to individuals? What is the informational content of that IRB that they hand to people when they agree to enter my database or participate in my study? It's not to say that you shouldn't be running a study if you can't figure out how to do it in a differentially private manner, but I think it's good to know. Yeah.
A slide or two ago, you mentioned that if you have a sense that differential privacy is adding too much noise, then there are some things to think about. I wonder, is there something that differential privacy can tell us that doesn't require intuition to tip us off that perhaps there would be too much noise or our algorithm isn't robust enough? Is there an algorithm, a number, a technique of some kind that can be applied?
Okay, good question. Yeah, so I think what you're getting at is that it's not just about the intuition. So actually, if one can prove a lower bound for the setting that you're interested in that says actually this is the best possible trade-off between noise and utility, that's a very concrete observation. And yeah, so there are a lot of people in this room who prove those sorts of bounds.
Or maybe the other question that I would say is, but is that good enough? And so not just this is the bound, but what would be the sense to tell us that under any possible query that I might run, that would be good enough, in fact, not just that it's the best.
Right, so I think what you're saying is, well, okay, so you get a bound, but that's, in many cases, worst case for, some particulars. It picks actually sort of a very pathological or sort of pessimistic, for example, set of queries for which you want to maintain privacy. And that's a space that people are actively exploring. So trying to understand as you move to sort of more specific sets of queries, for example, what are the possible privacy utility trade-offs versus with slightly more powerful, more general sets of queries, what are the trade-offs there? And then there's also the sense that so even once you get the set of queries right, maybe your data isn't worst case. And that's what I want to talk about now. But yeah, this is a great question. Okay, so yeah, what I want to focus on now is this question of what if your data isn't worst case? And what if you sort of expect that the study that you want to do is robust on your actual data, or the data that you'll probably get? And the first idea that I want to mention here is probably familiar to most of you as the concept of bootstrapping. So what do I mean by bootstrapping, for those of you who coming more from the privacy side of things? So what's the basic idea here of bootstrap aggregation? Basically, the idea is you're given a training data set, and what you do is you create from it many new training sets of a smaller size by sampling uniformly with replacement. And then what you do is you fit your model, you estimate your statistic on each of these smaller sets. And then you do some sort of aggregation. So you combine your estimates, your models somehow, voting, averaging, whatever it is, into some final result. So what's the motivation or the intuition behind this bootstrapping idea? Well, I would say, from my perspective at least, what's going on here is the idea is that a robust statistic should be stable on most reasonably sized subsets of the data. And robust is in quotes intentionally. I'm going to use a lot of notions of robustness, and we'll try and resolve them a little bit more formally shortly. And also, if a statistic is somewhat unstable, then this aggregation can actually help smooth your results. And if your statistic was very stable anyway, then the loss in precision should be pretty small. And so if we take this to privacy, there's sort of an additional interesting twist, which is that at first glance, if the function that you want to compute on your data set isn't low sensitivity, sort of in the worst case, but you suspect that it's usually stable, it's not really clear immediately how you should guarantee differential privacy, because so far we have tools that depend on the worst case sensitivity of your function. But actually, if your aggregation function preserves privacy, then you can get a differential privacy guarantee even when what you're aggregating are non-differentially private estimates. So bootstrapping has all these nice properties, and then when we move to the world of privacy, there's this additional nice thing, which is that it's a way, in some sense, to get privacy for free. It's a way of making non-private estimators, non-private functions, private, because you can run them on each of the subsets, and then you can do privacy-preserving aggregation. So this is the idea behind the subsample and aggregate framework, which comes out of work of Nissim, Raskolnikova, and Smith. And the way that they state subsample and aggregate is a little bit different than bootstrapping. So for them, what they do is they take the original database, they divide it up into non-overlapping small databases. We can return to this idea in a little bit. And so the reason they divide it up into these non-overlapping databases is so that any one individual only shows up in one of these smaller databases. And so any one individual actually only affects at most one input to the aggregation function. So they compute their desired function on each of these smaller databases. They do some sort of differentially private aggregation at the end, and then they get their output. So the good news about subsample and aggregate is that you can use any differentially private aggregation function that you want to, and the underlying function that you're computing doesn't have to be differentially private at all. The only restriction is that your aggregation function isn't allowed to depend on the actual data, because that would be another potential privacy leak. And it's really nice in the sense that private aggregation really just requires adding noise scaled to the sensitivity of the aggregation function. And then you basically get privacy immediately. Now, the sort of bad news on subsample and aggregate was that it might actually be difficult to bound the worst case sensitivity of your aggregation function depending on what it is. And if you don't really have a good sense of that, good control of that, the default is just going to be the max of its range, which is quite bad, potentially. And so it could be difficult to make promises of good utility using these techniques. But it's turned out to be quite a powerful technique. I've seen some nice applications of it. So for example, perhaps your underlying function that you wish to compute might be selecting the best model from among a set of M options. And then what you could do is on each of these sub-databases, you could compute the best model. And then your aggregation function could be a noisy max. So basically figuring out which of the models is recommended the most. And this noisy max is something that we can do quite easily in a differentially private manner. Basically, you just need to add Laplace of 1 and epsilon noise to each of the values and output the resulting max of these noisy values. You don't output all the counts. And privacy is actually pretty straightforward then. It comes just from sort of the monotonicity of the counts and this Lipschitz property that the counts can't change by very much when you add or remove a person from the database. So, sort of similarly, you could output a set of significant features. You could do sort of this model selection flavored types of questions using subsample and aggregate. Okay, so that was the first tool, this bootstrapping idea. If you expect that actually your real data is well behaved, that the study you want to do is robust on it. And the next idea in this context that I want to talk about is, well, what if you could check that actually your data is well behaved for the study that you want to do, and then decide whether to proceed. So the idea here is we'd like to be able to test in a differentially private manner whether a computation should proceed, and where should is this notion of whether the desired function actually has low sensitivity on your actual data. And if it doesn't, you should halt, and if it does, you'd like to be able to proceed. So what do I mean by a function having low sensitivity on your actual data? So the idea here, it gets called local sensitivity, very closely related to this notion of sensitivity. So we say that a function f has local sensitivity on a particular database D if local sensitivity of a particular value of f on a particular database D. If we look at all of the neighbors of D that differ in one person's information, and we see how much that function can change when moving to any of the neighbors. So if that is small, then in some sense, locally, this function is not very sensitive. We're in a database, we're in a place where actually this is a function that doesn't really reveal very much about the presence or absence of any of the individuals in that database. And so the idea here of this checking whether or not our function is well behaved on our data comes from work of Dwork and Ley in the form of the proposed test release framework. But the idea here is that you first propose a bound on local sensitivity. This is the level of sensitivity under which I'm willing to proceed with my computation. You then check whether or not the data that you have is low sensitivity in this local sensitivity sense with respect to this bound. And you do that check in a differentially private manner. Talk a little bit more about that. If it fails the check, you halt. And if it passes, then you can release the function with noise that's tailored to the local sensitivity instead of this sort of worst case sensitivity over all possible databases. And if local sensitivity of your function is much lower than the worst case sensitivity, then this could be a really big win. So what about this test idea? So this test could be asking the question, what is the L1 distance between my data and the closest database that fails the local sensitivity bound? And you notice that this test actually only has sensitivity 1. So this is something that we can do easily in a differentially private manner. And then maybe we want to have a sort of conservative local sensitivity threshold. So we want to make sure that even once we add some noise, we're getting, with high probability, the right answer on the local sensitivity. But it's going to be with high probability. And so sometimes this test could fail in the sense that because we've added noise, we've said something passes the local sensitivity test, but actually it didn't. And because of this, we can't get epsilon 0 differential privacy, but we'll necessarily have that additive difference, the epsilon delta type of guarantee. And it's important to note, I think, here that the level of noise that you choose to add, meaning the local sensitivity of the function that you're interested in, could actually be revealing. So it is really important that we do this check and proceed in a differentially private manner. So how is it possible that the amount of noise that you add could be revealing? It's not like you necessarily are announcing how much noise that you're adding. But intuitively think about a special case where an adversary knows that either the input database is D1 or it's D2, and actually it sort of intentionally hands you a function on which the two databases take the same answer. And the adversary even knows what that answer is. Now, if in return you respond with your mechanism with a value that's very, very far from the truth, then the adversary knows that the database that you were running that on probably had high local sensitivity. And so if D1 and D2 had very different sensitivity, actually the amount of noise that you're adding could be revealing. So actually it's important that we're doing this test in a differentially private manner. Okay, so one of the nicest things that I think comes out of the proposed test release framework is the observation that differentially private mechanisms don't actually necessarily need to be noisy. They can actually sometimes be perfectly accurate. This is really remarkable because so far I've been talking about all sorts of mechanisms that add noise or do something that perturbs the answer directly or indirectly. But it turns out that actually the proposed test released approach can be used to privately check whether or not your data is close to some other data set that's unstable. And if that's not the case, if you're very far from any unstable data set, then actually, in a formal sense, you're free to release the true value of your function on your data. And so this is really remarkable. This is a tool that says that actually, under differential privacy, sometimes when you have well-behaved data for the function that you're interested in, you can actually just release the true answer. So I've talked about, yeah.
How far you mean, like you said, you can release the exact true value of the function if it's too far from an unstable database or input.
Right.
What do you mean by far? How far you mean?
Right. So what's
can you
the
compare
metric?
this?
What's the metric there? So the metric there is basically, I think about Hamming distance between two databases. So how many entries would I have to go through changing in order to move from my current database to a database which is
In order to keep
unstable?
this epsilon steps, you still need to add some sort of noise, right? Or at least use an exponential mechanism.
So effectively,
According to
the
distance
the
score.
noise that's sort of the noisy aspect of this is this decision of whether or not to proceed. So there is noise in some sense. There's randomness in some sense, but it's randomness in the decision of whether or not to actually proceed with outputting the result of the function. Yeah. So there is still randomness there, but when you output the answer, it's the right answer, which is very surprising, I think. Very nice. So, okay. So I've been talking about robustness, and I've sort of quietly been using this word in a couple of different ways. So first of all, statistical robustness, which I haven't even really been talking about. But then I've had sort of robustness with respect to adding and removing a few points from the data set, and also robustness with respect to subsampling. And these are sort of the two notions that came up in these two tools that I talked about. So I want to talk briefly about a really powerful result that you can get when you combine these two ideas. And so this is work of Smith and Thakurta, sorry, I'm bad at pronouncing, which is a combination of this subsample and aggregate idea and this proposed test released idea. And basically the result that they have is that you can modify subsample and aggregate this approach so that it outputs the true function with high probability when f is subsampling stable on x. So you can check whether or not your function is robust in the subsampling sense and then output the true f with high probability when it is. And this is a really powerful and interesting result, I think, in part because of the consequence that effectively what they show is that differentially private model selection only increases the sample complexity of the model selection problem by a small factor that's problem independent. So I want to step back for a minute here and just mention that there's been a lot of work going on at the intersection between differential privacy and statistics, and many of the people who've been involved in this work are in the room. And if you're not, and you're interested in statistics on large data sets, I encourage you to talk to some of these people because there's really interesting stuff going on here. So some of the first work in this direction is work of Dwork and Ley, which sort of is the first step in making the connection between robustness in the statistical sense and differential privacy. And they have differentially private versions of a few specific statistical estimators, interquartile distance, median linear regression. There's been work on differentially private M estimators coming both from statisticians who are differentially privacy influenced and also more of an economics perspective. Some really nice work of Smith showing that for almost any estimator that's sort of well-behaved, that in a certain sense, the differential privacy adds asymptotically no additional perturbation. So this is a result that applies to MLE estimators, logistic regression, linear regression. So this is a very powerful result, basically saying that in many settings that you might care about in terms of statistics, differential privacy asymptotically comes for free. I think this is quite remarkable. So there's also been work on sort of the relationship between the convergence rate of differentially private estimators and gross error sensitivity. Some work on minimizing convex loss functions, which is relevant if you're interested in support vector machines and logistic regression. As I mentioned, there's been work on differentially private model selection. And in addition, there's been a bit of work, and I think there's even more than this, some work on some empirical investigations in the space of differential privacy and statistics. So there's a lot going on here, and I encourage you, if you're not sort of in this immediate community, but you're interested in running statistics on large data sets, to talk to some of these people. Because it's possible that what you want to do is actually really straightforward to do with differential privacy. And if it's not, that's also interesting. Okay, so one more objection that comes up a lot when talking about differential privacy to people who actually hold data is, well, hold on, I need to actually look at the data before I know what statistics to run. I have no idea what I'm going to do with this data until I see it. And this is incredibly common. And it should be obvious at this point that looking at the data and then deciding what statistics to run, even if you then run them in a differentially private manner, is not differentially private. The choice of the statistics could be revealing. So what to say here? I mean, I think it makes sense that sometimes you just don't know what's in your data until you see it. So one answer to this is that, well, can you look at your data in a differentially private manner? And so one answer to this is to start to look at these interactive type mechanisms that I was talking about before, where you can issue a query against the data set, get an answer, think about it, and then use that to pick your next query. And I think perhaps we should be thinking about hybrids between interactive and non-interactive mechanisms, where perhaps there's a phase, sort of we set aside some of the privacy budget in some sense for you to interact with the data and find out what it is that's going on there, what it is that's really interesting, and then we reserve the rest of the privacy budget for perhaps creating an artifact which supports what seem to be the most interesting questions on the data set, and then make that available. So I think there's some potential sort of combination that could be interesting there. And part of the reason for suggesting this hybrid is that I've heard over and over again, well, interactive mechanisms sound great, but who wants to be the entity that has to support interactive queries and maintain this interaction with the database from now until whenever we're done with it? And maybe the interactive queries are something that are more appealing on a short-term basis, some people have suggested, and then what we really want is some sort of non-interactive mechanism at the end, but perhaps we need to interact with the data a little bit to figure out what we want from it. The other thing that I wanted to say about this objection, I need to look at the data before I know what statistics to run, is that actually it's really great that we're talking about big data, because big data really force us to formalize what we mean by looking at the data. Because when your data is really big, looking at the data is not looking at the data. It's actually running queries on the data. And as soon as looking at the data has a formal meaning, then we can think about how to do that in a privacy-preserving manner. We can think about how to try to enable that in an interactive way. So I think because the data is getting bigger, it's an opportunity, actually, for people who are interested in privacy to go to people who are working on data and say, how do you look at the data now? What are the queries that you run? What is the process that you're going through in trying to understand your data, and what does it hold? And is this something that we can do in a privacy-preserving manner? So, just to summarize, hopefully you have some sense that privacy is something that's very easy to get wrong, and that differential privacy provides both a compelling definition and some sort of useful dose of paranoia about, about how things can go wrong. That powerful tools actually already exist, and some of them have really remarkable properties. Some come at no cost to privacy in a formal sense. Some come with no noise in a formal sense. These things are actually very surprising, especially if you've mostly heard about differential privacy in the context of naive noise addition. Another thing that I tried to highlight here is that you get some powerful intuition as well as some very powerful tools from thinking about robustness and the connections between these differential privacy-related notions of robustness, statistical robustness, and sort of what differential privacy is telling you about the robustness of the studies that you want to perform. And I wanted to hint that there are many tools that are nearly ready and quite relevant for common big data applications. And what I haven't said so far, but I think it's really the truth, is that there really aren't, however, ready-to-use commercial-grade type applications. So there's not differentially private static commands or whatever it is that you use that are available out of the box right now. And part of the reason for that is we have this sort of chicken and egg problem, that there's no demand until people realize that this is something that could be powerful and useful to them. And it's difficult to create the demand. And so I realize we're going to hear a little bit about some sort of differential privacy in the real world at this workshop, but I think there's room for a lot more of that. And what I hope that we, as a broad community, can do is to try and create more of this demand for tools. Yeah?
Katrina, towards this, who gets to pick epsilon? Is epsilon published? Do you think the adversary should know it, or is it private already? Or?
Yeah, so this is a great question, and sort of one of the basic questions that comes up as soon as you put a parameterized definition on the board. Where should that parameter come from? So I think the first part of your question is epsilon public? Sure, that's fine. Fine to make epsilon public. Sort of all aspects of your mechanism can be public except for the random coins that you're flipping. But I think the real question is, where should that epsilon come from? And I think in some sense it's good that differential privacy is not a definition that weighs in on this. Differential privacy is a guarantee, and the interpretation of that guarantee may be context dependent, but it does give us a starting place, and it gives us a way to turn a knob. I don't think that we yet have answers to this question, what should epsilon be? But we have tools that can help us start to understand what those answers might be. One of the things that's really nice about differential privacy is we understand these composition properties. We understand that it has nice post-processing guarantees. And so we can start to talk about how at least privacy risk aggregates or composes over time using these types of tools. But it's not clear, at least to me, that this tells you that the epsilon should be 0.2. But at least we have a starting place, and other people can chime in on this. Maybe this is a good question for the audience, because it's one that I know many of you have faced at various points. But I don't think that a privacy definition should necessarily tell you what level of privacy is appropriate, because I don't think there's a universal answer there. Yeah. Okay, so, yeah, go ahead.
I can wait.
No, go ahead. Question.
I want to make one comment related to that, two technical ones. One, it looks like the robustness notion that you were talking about is closer to resistance, the notion of resistance. That Tukey was very careful to make the distinction between robustness and resistance. And you're talking about resistance in some sense. The second point
What's
is
the
that.
definition of resistance?
Okay, yeah, can you
Give
give?
us some intuition.
That was exactly that. What proportion of the data is needed in order to change the value of the estimate in the large enough way?
Robustness
So it's
is
a
Sort of like
probability
influence?
the
distribution.
proportion
No,
of
not
the
even
data that is
breakdown points.
Okay.
So the mean
Okay.
is
That's
very,
well, okay.
the mean is very non-resistant, but you can take 1 over
Right,
n
right,
of the
right.
data.
That's what inspired the
It's
whole
exactly
connection to
this,
robustness.
no.
Robustness is about the probability distribution,
Right.
resistance is about the data.
Right.
It's
but it
about the
was-
data, it's a question about the data. The second thing, I wouldn't give up plotting the data, never, and looking at the data. And I don't think it has to, I'm sure it can be done in a way that will preserve the privacy. And in big data anyhow, we're working with flowers and things like that, and contours and so on. And the issue of privacy is not that, I don't think it's impossible to have this thing. The third thing is the comment that brought me to speak, and this is, I'm involved in the Human Brain Project, the European Human Brain Project, and part of it is building a database or utilizing database in this form. On the one hand, nobody heard about this issue still, about this private differential privacy and these issues, and there is a strong, there are strong requirements that data will not be moved from hospitals and so on and so on and so forth. On the other hand, it's a huge project. Among other things, there is an ethics committee with philosophers and people who are dealing with these issues. And we brought to them the question of privacy. And it's amazing that their answer was very much like the ones you proposed now. I mean, it's a question of the utility versus the level of privacy. And the larger the utility, the more you should be ready to will. You should be willing to give up on that. So in that sense, it fits very well this kind of thing. Of course, it's also interesting to know that the immediate answer was, well, what does the law say?
Sure. Yes. Yeah.
Only then they went into the second level of the utility versus the level of privacy and so on.
So yeah, so a bunch of really interesting points there. One that I wanted to draw out is that I haven't seen people thinking so much about differentially private visualization of data. It's sort of potentially an interesting direction to think in, because certainly
You have to solve it. I mean, we won't be ready to give that.
certainly there are tools that exist that should help in that direction, but I haven't seen that posed as the central question before. Yeah, I saw.
A couple of questions and an anecdote. I haven't thought about this stuff a lot, so forgive me, but partly I don't understand why the Hamming distance, because if you can tell that somebody almost like me is there, that's almost as good as telling whether I'm there. And secondly, if the motivating question of can you tell whether I'm there or not, it seems like the differential privacy actually solves this. I mean, it's great that there's a way to do it, right? This is wonderful. But it seems like it answers a slightly different question. A better question would be, how well can you test whether I'm in the database or not? And that's very different from this multiplicative bound, right? That somehow a testing distance seems like it would be more apt.
Okay, so these are good questions. So the first I think requires a clarification on my part. So when we're talking about Hamming distance between two databases, we're saying that there's a Hamming distance of 1 anytime we change
A row.
a row.
Yeah.
And it's not that
Even
the row
if you
has to
change it
be
by epsilon.
right. It's not
That's
that the
kind
row
of why
has to
I'm-
be sort of close or far.
Right.
You can modify your notion of distance, and it's perfectly acceptable to choose some other notion of distance and think
I think
in
some
that.
metrics on databases seem like the actual the thing you're trying to guarantee presumably interacts with how you choose to measure distance. I also have trouble coming up with a story that this exactly answers. Like, what's the real world story that this is?
For Hamming distance?
So here's like my favorite defense of Hamming distance, right? So take a utilitarian perspective. You're the guy trying to convince people to sign the waivers and give over their data to use in your study, right? If I can promise to you that sort of things that people learn from this study and any harm that can befall you will be roughly the same whether or not you sign over your data, then especially if I'm gonna, give you $10 or something, you are incentivized to sign the form.
So I should probably maybe defer this to Brave, but I'm having trouble with the attack model, right? So somehow the attacker needs to know that I'm in the database, or that either I am or I am not, and I'm trying to decide
No.
between two, right?
Yeah,
Because
that's-
how does my data don't necessarily identify me? What's the aspect of my row that lets you know that's me?
So it's about the presence or absence of an individual with a particular row. And I mean, if it's true, if you don't care whether or not anybody learns the presence or absence of your data in the database, maybe you don't
It's one thing to be able to tell
care.
that my data is there, and it's another thing to be able to tell that my data is there and I'm the person to whom the data belong.
There are many
Right.
attacks that show that
Right.
it's possible to use auxiliary information to take this thing that you don't happen to think actually names you and trace it back to you.
So I guess again, I'm
Right.
still trying to find like a really crisp attack model and like a whole real world story that goes with it. I understand that things that don't at first look like they compromise privacy might with auxiliary information, administrative records, so forth and so on. But I'm still just kind of missing, the precise scenario. And it's my failure to have read the literature completely and other things.
But it was
But
described so
the
perfectly.
So the other thing that what you were saying sort of hinted at is that there is also sort of, in addition to sort of this utility theoretic sort of interpretation of differential privacy that Aaron was maybe hinting at, there's also sort of a Bayesian interpretation. So there's a direct connection here between the differential privacy guarantee and sort of how priors are being updated. So
Let me, suppose that my row uniquely identifies me. And so the question is, can you tell whether my row is there or not? Why are we not using a testing metaphor? Like, how accurately can you test whether my row is there, as opposed to what does the presence or absence of my row change the probability of the results of various code? It seems like sort of a testing distance.
so that's.
Aaron wants to speak very
Oh, sorry.
So, I think one of the benefits of this definition is that it lets you say that, like, the thing that you might be concerned about is not just that someone will be able to test whether or not you're in the database, right? The thing you might be concerned about could be something very different than that, like whether you will be denied health insurance, which might happen whether or not someone can sort of prove that you are in the database or not. And differential privacy, in a sense, protects against whatever it is you might be concerned about, so that any bad event, like being denied health insurance, what the guarantee says is that if you sign the waiver giving up over your data, that's one universe, and in the other universe you don't. The chance that you're denied health insurance differs by almost a 1 plus epsilon factor. So if you had a testing-based definition where, like, the only thing you were...
Does that follow from the
It does.
definition?
Yeah, so that's a direct consequence of the
That's a
definition.
theorem, yeah.
Yeah.
But doesn't that depend on the functional form of how someone is using those data to decide whether or not to
That's
deny
one of
it?
the fantastic things about differential privacy, which apparently I should have emphasized much better. So if you have a differentially private mechanism, you can subsequently do anything you want to with the output of that mechanism, as long as that anything you want to doesn't involve going back to the original data, and that is still differentially private.
Okay, so
And
there's
so-
a measurability with respect to something.
It's the whole signal algebra and your testing critical region to be one of those sets in the testing.
Yeah.
So if M is a differentially private mechanism, F of M is also differentially private for any function F, no matter how complicated.
Yeah, so that's...
Applied to the upper.
Yeah, so that's the sort of one of the nice properties that apparently I really didn't emphasize enough, is this sort of post-processing idea that you can do anything you want to with a differentially private output, and sort of, even if it's something we haven't even dreamed of yet.
I'll beg people's indulgence and tell the anecdote now. It relates to the AOL thing. So I was the government's expert in the defense of the Child Online Protection Act in trying to find out how much pornography there is on the internet, how often people came across it in queries, how well filters block porn, and how much clean stuff they block accidentally. So this involved subpoena of search records from AOL, MSN, Yahoo, and Google. Everybody basically complied except for Google, who balked. This was at the same time that Google was giving results to the Chinese government But I started getting hate mail from around the world, basically saying I was trying to spy on people's searches, and this was some elaborate conspiracy involving Alberto Gonzalez to try to spend nothing. Anyway, it was very, very funny that these were queries with no identifying information other than the content. There was nothing to link different queries together. And in fact, the content of the queries wasn't the issue. The issue is what happens when you actually run the query. What do you get back, and is it pornography or is it not pornography? But it was a very interesting time.
Interesting. So I don't know how how much we want to respect the schedule. Should we continue to take a few more questions? Okay.
Are there sorts of online mechanisms for assessing what happens with adding a new data point to an existing data set? So the picture I have in mind is you have somebody who knows that they're probably quite an outlier, and even if there's some epsilon delta guarantee, they're worried that the delta is really going to hurt them, and then they'll be identified. Or maybe for typical data or this very data set, it's okay until they're added, or something like that.
Yeah, great question. So I didn't get a chance to talk about it, but there is a literature on differential privacy in the streaming setting. And so,
It will be covered in a survey.
oh yes,
by Alex.
yes, and you will hear about it which day?
Friday.
Friday. There you go. But great question. Yeah.
So you brought it up briefly before, but you didn't talk about the concept of any functional form. So one could think of an extreme situation in which there are only k columns, and each column is a category. So there's a set universe of possible values for people. And therefore, you could define a function, and let's say you know everything about the universe, so you know that it has this incredibly high dimensionality and individuals belong at points in the universe. So if I can have a query, I could think about trying to define a query question at an atomistic level that would tell me whether or not somebody was in a database or something else. So your statement of differential privacy on any functional form would seem to imply that that's not relevant, and I don't quite understand why that would be a problem.
Great. Yeah. So the question that you described is going to be, for example, very high sensitivity. So basically, if you want to be able to specify a question that goes from, no when I'm not in the database to yes when I am in the database, in order to do that in a differentially private manner, you're going to need to mask the difference between the no and the yes in a very strong sense. So you're going to need the probability of a no to be very, very similar to the probability of a yes. So there's going to be very, very little signal left if you want to answer a question like that. More questions?
Earlier in the talk, you spoke about accuracy of a differentially private query. Can you give some examples of how accuracy is measured?
Sure, yeah. So that's something that may depend on the context that you're interested in. So for example, if we're in the space of numeric queries, you might just be interested in the difference between the answer that you give and the true answer. If you're answering a large number of queries simultaneously, you might be interested in the average or the worst case over the set of queries of that difference. But when you're in a setting where your output is something more sophisticated, so you want to solve a combinatorial optimization problem or something like that in a differentially private manner, then you have to think about what's the right notion of accuracy. What does it mean to get a good answer to this problem? And then you define your accuracy metric, and then you sort of see what you can do trading off against privacy there. So there's not necessarily one answer to what's the right accuracy metric. It's something that you're going to pick based on your context.
Okay.
So I'm going to take the opportunity to do a brief advertisement. So maybe less for this audience because I think I've covered most of the material of this paper, but if you know people who might be interested in an introduction to these ideas, I've recently written a sort of survey/opinion paper called Privacy in Database Research, intended to be an introduction to the notions and some of the issues motivating differential privacy, some of the tools, focused on an audience that deals with data. So you can look it up on my website or on SSRN, Privacy in Database Research. All right, thanks for all the great questions, everybody.